Now, the factor theorem states that if you substitute x equals 5 into that equation and you get a result that fx equals 0, then x minus 5 is a factor of that expression. Now, that's probably not true in this case, so I'll get rid of that. But we've got to prove that x minus 3 is a factor. Well, to find out whether that's true or not, we need to substitute x equals 3 into fx. The rest is arithmetic. What do we get? So I've popped in x is equal to 3 throughout the equation. Resolving all this lot, we get 108 for 4 times 27 minus 108 for 12 times 9, and the 6's cancel, and this is indeed equal to 0. So we've done part A. Part B. Hence show that 3 is the only real root of the equation fx is equal to 0. Well, what have we proved so far? We've proved that the curve, whatever shape it is, goes through the point x is equal to 3, crosses the axis at x equals 3. That's after all what a root is. They've now asked us to show that x equals 3 is the only time it crosses the x-axis. So we've got fx, and this is equal to a factor that we've pulled out, which is x minus 3, multiplied by a quadratic. So I have to write that down in its general form. So this is ax squared plus bx plus c. Well, the values of a and c pop out extremely quickly. Look at those two multiplications. The x multiplied by ax squared is the only multiplication of these brackets that produces the x cubed term. So we can say ax cubed must be equal to 4x cubed. Therefore, a is equal to 4. And the same argument applies to the negative 3 multiplied by the c. This is the only multiplication of those brackets which offers a numerical answer. So I've got a second equation here. Negative 3c is equal to negative 6. So therefore, c is equal to 2. But now we've got to do a little bit more work to find out the value of b. And you can do that in two ways. You can find out what multiplications of those two brackets offers an x squared term and equate that coefficient to negative 12, or indeed what multiplications of those two brackets offers an x term. Let's do the x squared ones. So I've got negative 12 x squared from my function. Now I've got to find all the multiplications that offer x squared. Let's do them one by one. I'm going to multiply x by each one of these terms and see if I get an x squared term. Multiplying that by a... No, that doesn't work. Yes, I've got my first one here. There should be two. I've got x times bx, so this must be equal to bx squared. Going on, x times c, no, now the 3. Yes, this one produces another x squared term. So this is negative 3ax squared. We can knock out all the x squareds and get, therefore, negative 12 is equal to b minus, a is 4, so this is negative 12. So therefore, b is equal to 0. There is no x term. So I can now express fx as x minus 3, and then filling in all the results we got, 4x squared plus 2. So we know that x minus 3 is a root. We now need to find out by setting this guy to 0 whether this produces any roots. We're testing it. What value of x produces a 0 answer? Divide through by 2 and get 2x squared is equal to negative 1. X squared is equal to negative a half. And if we attempt to find the square root of both sides of that equation, we can't, because we cannot take the square root of a negative number without going into complex numbers. So I can say that x equals 3 is the only real root. And indeed, this curve, I don't know whether I've drawn it anywhere near correctly, going from negative to positive, but no, this point here is the only point that the curve crosses the x-axis. There are no other real roots. And that's the answer.